Hello, this is Chris Cantalupo. I'm a developer of the GOPM software package, and today I will be presenting the tutorials for that package, and in particular the very first step in that tutorial, tutorial 0. On the left here, you'll see the GOPM Git repository on GitHub, and if you navigate in this web page down to the tutorial subdirectory, you'll see the code that we're going to go over, and also a README down below that identifies most of the information that we'll be conveying in this video. So today we're going to go over these first few sections here on tutorial 0, and please feel free to go to this link and follow along there. Okay, thanks. And now let's take a look here at our cluster system that we're running on here. I'm in the Git repository now in the tutorial subdirectory here, and we have the GOPM package built and installed into my home directory. In particular, if you look in home build GOPM, this is the default location for the install as it's set up in the tutorial scripts. And you can see there that the package has been installed there, including the shared object libraries and our headers, etc. Okay, so once the package has been installed, you'll look in this tutorial subdirectory and you'll find first the README. So let's just take a look at that in plain text here that we're going to be following along with. And you see that there are different sections. Each section has an associated source file written in C and a script file that will execute that source file. There's also a tutorial env bash script which sets up the environment for locating the GOPM package. As I said, by default, it looks in your home directory in the build GOPM subdirectory. That can be modified if you've installed to a different location. Um, in order to build the tutorials, there are two different scripts that are there. These scripts and the make file that's in the tutorial subdirectory is a completely independent build from the GOPM package. The GOPM package uses auto tools and has a configure script. It's a much simpler build system in the tutorial subdirectory so that users can understand exactly how things are being built. So the scripts for the different tool chains, the GNU tool chain and the Intel tool chain, can be used to build, and if your environment's set up to support those tool chains, it should work transparently. If MPICC is not in your path, then you have to set this environment variable, all caps, MPICC, in order to build the tutorials. So if we run the script, I'm using the Intel toolchain, and if we build the tutorials with the tutorial build Intel script, you can see that it's already been built here, but if I make clean and then run the script again, we can watch it be built. Okay, and tutorial 0 is what will be the focus of this video. And this is going over the very first step that an HPC application developer or user will want to do when they're integrating with the GOPM runtime. In this example, there are no calls into the GOPM library within the application. It's a completely unmodified application in that regard. And we're using the environment variables identified here in order to enable the GOPM runtime. This first environment variable, LD preload, is how we get our symbols injected into the executable. And it's important to also set the LD dynamic weak to true, which enables weak symbols through dynamic linking. And when you LD preload our library, this interposes on the MPI PMPI interface for getting our runtime up and running. This environment variable here, GOPM PMPI CTL equals process, identifies that the controller should be launched using one MPI process per compute node. There are several other ways to launch the GOPM runtime, but in these tutorials we use this method because it's pretty straightforward and easy to explain. But please look into the documentation about other methods for launching the GOPM runtime. Okay, and these last two variables, they identify the output files that GOPM will generate from the controller. One is the report, which is a summary that will be created at the end of the application run. And the trace identifies telemetry information throughout the run, and that that has a lot of information that you can dissect to figure out exactly what happened during the runtime. Okay, so let's take a little look at tutorial 0.c. It's a very simple application. Here you can see that in the main, there's a call to initialize MPI, and this is how the GOPM runtime is started up. And the GOPM runtime removes one of the MPI processes from CommWorld, so that when we then call MPI CommSize on CommWorld, we'll see that reflect one fewer processes per compute node than you might expect from the command line arguments that were given to launch the executable. And here we see that this application simply finds the size of the world and prints it out, sleeps for 5 seconds, and then calls MPI finalize, which shuts down the GOPM runtime. Okay, so let's see how that works. If we export our MPI exec environment variable to use Slurm's srun to launch, and we use Slurm's method for binding those processes to particular CPUs, which is a requirement that GOPM has, that each application process is bound to a unique set of CPUs. And then we launch using 2 nodes. If we then execute the tutorial 0 script, we could take a look at that quickly before we execute it. In the script, you see it just has a reflection of what's in the README in terms of setting these environment variables and then launching the tutorial 0 executable. Additionally, in order to get this GOPM libdir, we source the tutorial emp.sh, which points us to where GOPM is installed. Okay, so then if we go ahead and run that, we're using 10 ranks total on 2 nodes, and we'll see that when we run that, we see our 10 ranks and their bind mask. And you see that MPI reports that the COM world size is 8, and that's because GOPM has taken 1 rank per node for running the control algorithm. So even though we set n equal 10 here, we're seeing that MPI COM world size is being reported as 8. It sleeps for 5 seconds and then it outputs our results. So let's take a look at that. You can see that this experiment ran on our 2 nodes, Mr. Fusion 1 and 2, and we will see reports and traces that reflect that. So first, let's check out the reports. And this is named in this way because of how we set this GOPM report variable, GOPM 0.report. And then it's appended by a dash and then the host name where the report was generated. So for our first compute node, we'll see that this is reporting that the runtime was just about 5 seconds. We consumed this many joules of energy, and the clock frequency was running on average at 107% of the Intel sticker value. That is to say, it's been turboing. Okay, and if we look at the same report from the second compute node, we'll see similar numbers, not exactly the same, but this is a similar report coming from the other compute node. If we want to take a look at the trace files that are generated, it's useful to make our window a little bigger because there's quite a bit of information in this text file that is pipe delimited. So if we take a look at tutorial 0 trace for Mr. Fusion 1, you'll see that the first row, which is still wrapping here, it identifies the names of all the fields. The region identifier is the hash of the region ID. This is second since the application has begun. There's a sequence of telemetry values that are collected from the hardware for each domain of control. In this case, a package. We have 1 package on the system, and we see the package energy, DRAM energy, frequency, instructions retired, clock unhalted core, and clock unhalted ref values, and the read bandwidth. And the last values here, which are not directly from hardware, come from the application itself. It may report progress and runtime. There's also the policy which GeoPM is enforcing, and so that's described here in the mode, flags, number of samples, and power budget for that policy. Um, and this can be parsed with a number of different options, anything from Excel or, if you will, awk or Python. Pipe delimited files are pretty easy to parse. So although the Thorian is a little big, it's easy to take that and analyze it in a variety of applications. Okay, well that about summarizes the tutorial 0. Um, and next time, when on the next video, we'll talk about a slightly more realistic application, which has some regions that do some computations, and we'll show that application next. All right, thanks for joining.